The way energy and momentum are connected in relativity is a pretty big change from Newtonian physics. Back then, it was just kinetic energy is equal to p squared over 2m. That's another way we could write it. But instead of that, we get a relationship that looks a lot like the space-time interval. Here we have total energy squared is the sum of the squares of each momentum component times c squared plus m squared times c to the fourth. Now, the reason our minus sign is gone is we sort of wrote this the wrong way. What we should write is m squared c to the fourth on this side, and then e squared minus all the momentum stuff times c squared here. Notice that we have three negative vector pieces and one positive scalar. And before we wrote the space-time interval, we wrote it as x squared, y squared, z squared minus ct squared. Really, we should do one or the other of those things. I shouldn't mix them in one course. It's not going to hurt us now, but it's just sort of bad style. If you look at a relativity book, a lot of times in the introduction, they will say which of these conventions they're going to use. For example, they might call it plus, 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 minus, so the three space parts would be positive and the time part would be negative. Or they might do space parts, the three things, negative and time positive. They might also put time first and call it negative and positive, 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 or the opposite of that. It doesn't change the physics. It changes how you write things. So we notice a few things. First of all, if our definition of P is mv gamma, we could do a little bit of algebra and see that we can also write the total energy as mc squared gamma. Now, compared to the Newtonian case, we still have a value for energy even if something is not moving. For example, your own mass in your own frame, you would say gamma equals 1, but you would still have an energy equal to mc squared. That's a ridiculous amount of energy. 1 kilogram of mass is equivalent to about 9 times 10 to the 16th joules. Einstein is most famous for this equation, E equals mc squared, but that's not the real equation. It should be E equals mc squared gamma, or E equals square root of pc whole thing squared plus mc squared whole thing squared. The key change here is that mass is invariant, so everybody has to agree on E squared minus P squared C squared, but it's not conserved. That means it can change in time, and this is another crazy thing in relativity that we wouldn't be expecting. Chemists use the law of conservation of mass because if you put 23 grams of sodium and about 35.5 grams of chlorine together, you get 58.5 grams of salt. In reality, when you do this, you're going to release about 800,000 joules of energy, and that energy has to come somewhere. If you want to separate the salt back into sodium and chlorine, you'll have to supply 800,000 joules of energy. What really happens when you combine the two quantities above, you get less than 58.5 grams, but it's less by this tiny amount, 800,000 joules over c squared. That's about 9 nanograms. It would be essentially impossible to measure. That's the reason why, even though it's not really a law, the chemists can get by with saying there's a law of mass conservation, because in general, to the best of our ability to measure, mass is conserved in a chemical reaction. In fact, in any chemical reaction, if we could accurately measure the masses of the products and reactants, we would see they aren't exactly equal, and the difference is going to depend on the energy released or absorbed divided by c squared. Even for really energetic chemical reactions, there's not enough energy involved for this change in mass to be noticeable. Nuclear reactions, on the other hand, are in the ballpark of 1,000,000 times more powerful than chemical ones. If you look at the first atomic bomb dropped on Japan, the energy release was incredible. It was about 63 trillion joules. That's the equivalent of about 15 million kilograms of TNT. Now, the bomb itself had a mass of 4,400 kilograms, and only a tiny, tiny part of that actually reacted. If we had some way to collect all the tiny pieces of that bomb that were blown everywhere throughout that city and bring them all back together and get their mass, what we would find is it was about 0.7 grams less than the starting mass. So destroying that entire city meant we take the energy equivalent of the mass of a paperclip. So mass is a very, very efficient way to store energy. Converting matter to energy can happen on the small scale, like in chemical reactions, or on the large scale, like in something you may have heard of called a PET scanner. In this scan, you're given a radioactive chemical that has a biotracer on it. It goes to some interesting part of your body and it emits antimatter electrons, which are called positrons. The positrons find an electron in the neighboring tissue, and the two of them completely annihilate to form generally two, sometimes three, gamma ray photons. Particle accelerator runs the same idea backwards. We take protons or electrons and give them ridiculously large amounts of kinetic energy, smash them together, and we find new tiny amounts of matter there. We can use these conservation laws and the relationship between energy, momentum, and mass to figure out an interesting question, and that is, can a free electron absorb a photon? If so, we'd say our incoming pieces are an electron and a photon, and the only outgoing thing would be an electron. To make life easier, we're going to set c equal to 1. You do this a lot of times in physics. If, for example, we chose feet and nanoseconds instead of meters and seconds for our distance and time, we'd get almost c equals 1 exactly. Now we can just write E equals m gamma, and our interval looks like this, E squared minus P squared equals m squared. The electron's mass we can write as me, and we have to pick some velocity for it. We don't lose anything if we pick its velocity as being equal to 0, because the only other thing involved is the photon, and whatever speed we pick for the electron, it will still say the photon is moving at c. This is our second postulate. There may be some redshift or blue shift, but we haven't picked an energy yet, so it doesn't really matter. If we put V equals 0 for the electron, we also get P equals 0. This means the electron's total energy is just its mass energy. For the photon, on the other hand, we know m equals 0, and therefore energy and momentum are equal as long as c equals 1. If we made this a low-energy visible light photon, in terms of the electron mass, that would be 0.00001 or something like that. Again, we don't really care about the energy, so we can make the math easier by making it a high-energy gamma ray. We'll make its energy equal to the electron's energy. So we look at our incoming stuff, the energy, momentum, and mass of each of the things. We have energy of m, mass of an electron, for both the electron and the photon. For the electron, no momentum. For the photon, momentum equal to mass of the electron times the relevant c. And the masses, electron mass, and 0. Since energy is conserved, what we have on the top left of the green bar, we have to have on the right. So me plus me equals 2me for the electron's energy when it leaves. Momentum is also conserved. So the incoming momentum, which is me, has to be the outgoing momentum, which is me. You might think the last part is the easiest. We just plug in me, but we don't have a conservation law for mass. The way we find mass is solving this interval equation. So m is the square root of e squared minus p squared. We put those things in, and the answer we get is the square root of 3 times the mass of an electron. So that means we can't do this because that's not the mass of an electron. It's really just me. We can't have a free electron absorb a photon because we can't conserve both energy and momentum. That also works the other way, so a free electron can't spontaneously emit a photon. There has to be an atom nearby or something. The electron can scatter, which generally means reflect a photon, but it can't keep it. This means we would expect free electrons to be reflective if we had some place where we had a bunch of free electrons. It turns out we do have them in metals, and if you think of what's the first property you think about that just about all metals have, they're shiny. Now, the last part of this, we'll look very briefly at general relativity, and the reason is it's very complicated. You could spend a semester on it in grad school and still not know a fraction of it. There are a couple of basic ideas that are really neat, though, that we can look at. First idea is if we only make measurements at one point, we call these local measurements, we can't tell the difference between being in a box on the Earth and being in an elevator that's being yanked upward at 9.8 meters per second squared. All of our experience from the first semester will give the same results either way. And the classic example is measuring g by dropping a ball and timing it. Now, of course, if we measured at more than one place, we would detect a difference because on the elevator, both balls will fall straight down and they'll be parallel the whole way. But on the Earth, they actually both fall towards the center, so the balls would be getting closer to each other. Now, for a reasonable elevator, this is a ridiculously tiny change, but still. If this is true, then think about what happens if we have a tiny window in the elevator and somebody shines a laser through it. As the light is crossing the laser, the elevator will obviously move up. It's still moving, so it's going to hit, the light spot will hit a little bit lower on the right side than on the side with the window. Extremely small difference, but it's still there. If that's true for the elevator, it's got to be true for the Earth. What this means is light falls, or we could say it bends, in a gravitational field. This is a super tiny effect, but it's been measured many times. Now, if you remember refraction, we found that light bends when it changes speed, and it curves towards the low speed region. The same thing happens here, and the reason is that time itself is what's moving slower, closer to the surface of the Earth than far away from it. The magnitude of this is ridiculously small, but it's important. And oddly enough, it doesn't depend on the gravitational field, but on the gravitational potential. Potential is, remember, the gravitational version of voltage. Keep in mind the difference between potential energy and potential. If we're close enough to the Earth to get by with using little g, then the potential difference between 2 points is just g times h. This is potential energy divided by mass, remember. The time dilation factor is this 1 minus gh over c squared. What that means is if we had a 1 kilometer building, which is taller than anything currently existing, the clock would run faster than a clock on the ground by about 1 part in 10 trillion. That means if you spent 32 years on the top floor of the building, your clock would be 100 microseconds, or a tenth of a millisecond, ahead of the one on the bottom. Obviously, this change is completely unimportant for most of daily life. Now, as tiny as that is, this has been measured repeatedly using atomic clocks. One test involved putting 2 clocks on planes and sending them around the Earth in opposite directions, and then measuring the difference in the time they read when they were brought back together. And of course, it matched the prediction. Places where this factor is important is if we're near a black hole or a neutron star. And in fact, years ago, before there was as much collaboration in science as there is now during the Cold War, what we call black holes, the Russians called frozen stars because they were formed during the collapse of a star. And when the star collapses to a certain point, the gravitational potential is so intense near it that someone far away would say time has stopped for that person falling in with it. Therefore, falling into a black hole would give you a chance to see how the universe ends, since as far as the rest of the universe is concerned, it'll take you an infinite amount of time to fall in. Now, for you, it'll be over in a very short time, and you can't send messages to anybody about what you saw, so probably not a trip you want to make. Now, at this point, it would be reasonable to be skeptical about all these giant changes to Newtonian physics, and you might also feel like, why did we spend a year learning that stuff to find out it's not right? First, keep in mind that for almost every purpose, including orbital dynamics of satellites, Newtonian mechanics is plenty good enough. It's a really hard measurement problem to find places where there's a difference between Newton and Einstein big enough to detect. Now, is this anything that could affect your life, or is it just scientists in some faraway lab? To answer this, think about the global positioning system. The basic idea is there are a few satellites orbiting the Earth in a configuration that means there are usually a few in your part of the sky. These satellites are essentially atomic clocks with radio transmitters, and they send out information that your phone or GPS unit picks up, and it's using the time difference between the signal arrival of each satellite to locate your position on the globe. This requires using the travel time of light, and therefore the timing is critical here. If you want to know your position to within 10 feet, you have to be able to measure times to better than how long it takes light to move 10 feet, which is 10 nanoseconds. Now, what if Einstein had discovered special relativity, but no one had discovered general relativity by the time people got the idea to set up a global positioning system? The satellites would have had their clocks corrected for their gamma factor before we launched them. If we send up an ordinary atomic clock, Once it's moving, we'd say, no, it's slow. It would be slow by 7 microseconds a day. So what we have to do is make it fast by 7 microseconds a day while it's sitting on the surface of the Earth. Then by the time we get it in orbit, we take care of that special relativistic shift. If we don't, losing 7 microseconds a day corresponds to an error of 7,000 feet, which is more than a mile every day. So let's say they knew about special relativity, they sent up slightly fast clocks, they didn't know about general relativity. If you're at the altitude of the GPS satellites, the gravitational potential is such that the clock would be too fast by 46 microseconds per day. That means if we just corrected for special relativity, we'd lose 9 miles a day in accuracy, and it would be 9 miles every day. You'd be able to guess your position better than that. Because these effects are in opposite directions but not the same size, we make the clock in a GPS satellite so that on Earth it's 39 seconds slow every day. We put it in the correct orbit, and the two relativistic effects that don't quite cancel would cancel that 39 microseconds out, and we have a working GPS. So if you've ever used your phone or a GPS system to figure out where you are, you've done a very precise test of both special and general relativity.